some reason it is just going round and round. What did it say? Yeah, it is started. Okay, good morning. So let us begin for today's class. So as usual, thank you for coming on a weekend. Yeah, and since we have spent a lot of time doing the preliminaries, it was necessary to catch up. So anyway, so let's commence. So let us begin by asking if there are any questions from previous class. Does anyone have any previous questions from previous class?
Sir,
Oh,
I have one.
yeah, please go ahead.
Sir, in the last week, when we were talking about the stopping criteria, like convergence, you
Mm-hmm.
said that we can check for that argument.
Mm-hmm.
Uh,
No, I said when we were stopping criteria for K means, right?
yes, sir.
So okay, let me just. So what is the question? Can you repeat once?
Sir, I was just thinking about it, so I just thought that if we are already recomputing the centroid, then wouldn't it be expensive to recalculate that for stopping?
Yes. So you can remember the previous centroid, right? So you can have centroid old and then centroid new, and then you can see how much it has changed or something like that.
No, but our convergence calculates the points calculates the distance of centroid from each point inside the cluster, right? So
Yes, yes. Okay, so you can look at the distance change as well as either that, or you can look at the centroid. So what is the question? I don't understand.
हाँ
Both of them
हाँ
are fine.
so I was saying कि if we just consider the change in the centroid position, so that would be economical rather than checking the square every time, square from all the points every time.
So you are anyway having to compute that, right? See, what you are going to do is you are finding the minimum distance with respect to every centroid. So let me just explain again. So anyway, I have to recall k-means. So I will just come to your question. So let me just write down these things, okay?
Yes, sir.
So Siddharth, it will come to it. Okay. So now k-means we said there are two versions, right? So let us write both the versions. K means both are identical. There will be no particular difference in each of the performance. Okay. Besides this question, does anyone else have any questions? Okay. So basically, K means if you remember, let me just draw here so that if you have just somehow forgotten about it. Essentially, what you have is there are some set of points, and what you would like to do is you would like to cluster it into three groups, such as one group here. One desirable cluster could be something like this. Okay, so what is x and y axis? These are two features that I have shown. It's only representative. So in general, each of these points could be residing in a high dimensional space. So this is residing, the points are residing in a two-dimensional space, but in general, it could be residing in a high dimensional space. So what is the input? So for both of this, so I will, let me just, so K means let's not distinguish the version as yet. So first let us see what are the inputs. So input is K, okay, K equal to 3 for example. Okay, so this could be K equal to 3, and output will be the centroids. Okay, so centroids or means, which are called as mu1, mu2, and mu3. Okay, and the points are of course also xi. All the points are there. I equal to 1 to n. Okay, and each xi belongs to R2 in this example, or in general, it belongs to RD, some high dimensional, I mean, some larger dimensional space. Okay, so this is what it is in general. So once you find the means, so what you are going to also get associated is the cluster allocation. So this is one, and then you also have ZIs. Okay, so the ZI is also an output where ZI is equal to J implies ith point belongs to the jth cluster. Okay, so this could be also a way. Okay, so this zi can be 1, 2, or 3. Okay, so sometimes like you have seen, sometimes we will denote it as just to be more clear, we will have zij equal to 1 instead of zi equal to j. So these kind of things might happen. So if I ith point in jth cluster, so we will sometimes use this notation as well. Okay, so one of the things that you should get a little comfortable is the notations will keep changing. Okay, not because we want to confuse you, because it's very difficult to have a consistent notation across various references. All right, so that is the whole idea, but I think you should be fine. So if anything confuses you, you please let me know. Okay, so this is what we saw was k-means, and then I said there are two variations. So let us write the two versions. So version 1 and version 2. So in version 1, both these versions, initially what we do is we choose mu 0. So this 0 in the subscript indicates my current estimate, okay, of the centroids. Mu 0 and zij0, okay, randomly. Okay, so basically choose. Okay, let me write this. So pick. So this is my initialization step. So similarly, we will have pick. Okay, so now what we do is we will repeat some steps till convergence. So we will come to the specific question Siddharth was asking about. How do we tell what is convergence? But let us defer that discussion. So repeat till convergence. So now, assuming that mu 0 is correct, okay. So zij, what we will do, we will say zij is equal to 1 if, okay, the distance between the xi minus mu j, okay, zij of t plus 1 is equal to 1 if the distance between zij sorry, xi and mu j estimate at t. Okay, so this distance, the Euclidean distance, is minimum. 0 otherwise. So this is my allocation for zij. This is let us say part A, and in part B, what I will do is once I have these zij's, I will recompute mu j's. So recompute mu j. Okay, so let us just mu j of t plus 1, the current estimate. So these steps, these two steps, we will repeat till convergence. Okay, so these two steps are how it will go. So this is version 1. In version 2, we have the same thing. So repeat till convergence. Okay, all we are doing is we are interchanging these steps. So this doesn't change anything. Okay, so we can say recompute mu j of t plus 1 using zij of t. Okay, so repeat till convergence and you keep track of t. Okay, increment like the loop variable properly. Okay, increment t. So start with t equal to 0, then you keep incrementing it. So this is what you do in step A. In step B, what you will do is again the same thing. Zij of t plus 1, okay, is equal to 1 if the distance between xi minus mu j of, this time you have to use the updated value, t plus 1 is minimum. So essentially both the algorithms are same, just that the steps have been interchanged. And now coming back to the question of convergence, I'm sorry, I wrote some convergency here. I meant to say convergence. Okay. So now coming to the issue of convergence, so there are two things you can do. See either what is the difference between mu j of t plus 1 minus mu j of t. Okay, this you take sum over all the clusters. This change, if it is less than epsilon, you stop. Okay, so epsilon is a parameter you are choosing, or you keep track of like number of zij changes. Okay, so whenever you are making an allocation like this, you compare with zij of t, and if there is a change, you increment a variable, and then you see number of changes. If the number of changes is less than some k, then you stop. These are the two ways I can think of how you can stop. So now, Siddharth, what is your comment, or is it clear now?
Sir, I think I got confused. It's clear now.
Okay, good. So anybody else has any questions here? Okay, so I'm not hearing anything, so I'm assuming things are clear. Okay, so now, yeah, okay. So now we have to generalize this. Okay, so basically, k-means is a clustering method, unsupervised method. Now we want to come to our original problem of Gaussian mixture densities. Okay, so what we had was, I told you that on general Gaussian may not necessarily be capturing the variation in the population. Sometimes it could be something like this. Okay, which is saying that there are three different populations here. Okay, this is like your population 1. Okay, and this is population 2, population 3. So yesterday I used the notation of lambda. So with your permission, I will change it to pi. The reason being, this is what is there in Bishop and many other textbooks. So I just want to be consistent. So I hope you wouldn't get too confused with this. Okay, so this is f1 of x given mu1 sigma 1 squared. Okay, plus so just for making our lives a little easier, I will only take two clusters. Okay, it generalizes pretty easily. Let's just take two clusters. Okay, so this is what are the mixture proportions. This is pi 1 and this is pi 2. Okay, so this is what is our density of f of x. So this is f of x. Okay, so it's coming from two populations, and so the populations, the things that are hidden, so z1 zi's are hidden. Okay, so the data that is given to you is actually x small x size I equal to 1 to n. Okay, so some points like this, a few points here, a few points here, a few points here, things like that. So this is given to us. You don't know this shape, right? Because that is what you are supposed to be learning. Okay, so now typically when we did MLE, what did we do? So we took the likelihood and then we tried to find what parameters maximizes it, right? So that is what we did. So the same approach we will try here, and we will see what is the difficulty that we are going to face. Okay, and then we will try to do something, and then it turns out that that simple step actually is a more powerful algorithm. So that is what is the plan for the rest. Okay, so you will see why I brought k-means anyway. Okay, so anyway, k-means is an important algorithm, important unsupervised algorithm on its own, but it has got crucial connections with EM also, EM and Gaussian mixture models also. So that way, talking about k-means at this point is useful for you. Okay, so let's try to do MLE for estimating the parameters. Okay, so my parameters theta are actually pi. Pi means there are two of them, pi 1, pi 2. Then there is mu, which is mu 1, mu 2, and sigma squared, which is sigma 1 squared, sigma 2 squared. So this is how are the parameters that I wish to learn. Okay, so now let's try to write the likelihood. So likelihood of the data x, okay, given these parameters, like, So likelihood is a function of theta, right? So given some theta and your data, okay, so let me write that as yeah, data. Okay, so this is what I would like to maximize, right? So first we have to write what's the likelihood. So that is nothing but product of all the individual points, because they are all independent. That is the assumption we make for these cases. So the general case, you will see there are plenty of examples like hidden Markov model or LDA, latent Dirichlet allocation. Those things will be part of your mini project. So you will get to try out those, and there also we will use EM. Okay, so those things you will see. So what you are having there after that is f of xi. Okay, and the xi's are coming from the hidden parameters. So here, though I have not written it, the whole dependence is on pi I, mu I, and sigma I, right? So that is what we call it as theta. Okay, so this is what it is. So let us just take the log likelihood and see what happens. So the log likelihood, small l, is summation I equal to 1 to n. Okay, so now if I want to find out xi, okay, so xi itself can belong to two of these points, any of these 2 points. It belongs to the first cluster with probability, so ln. So here it belongs to the first cluster with probability pi I. Okay, so this is the same. This is not really anything different, but it is just this. Okay, so I'm not writing the rest of it, but you, okay, maybe I should. For the first time, at least, let me write xi mu1 sigma 1 squared plus pi 2 f2 xi mu2 sigma 2 squared. Okay, so is this clear for everybody what has been done? Does everybody follow this step? Can I just quickly check? Can you please say if it is okay so far? Things are going to get quite complicated pretty soon. Okay, so that's why I'm checking with you. So every step here will be required later on. You will see that it is more and more things will be required. Okay, very good. So now this is what it is. And then in order to really find the MLE, what we do is we take the derivative with respect to all the parameters that we wish to estimate. And we try to set it to 0 and see what happens. Okay, so there is one additional constraint that is coming in. Okay, so basically my theta MLE is argmax of L of theta. Okay, where theta actually, I'm just writing what is theta. Theta equal to pi mu and sigma squared. This is what it is, but there is an additional constraint subject to pi 1 plus pi 2 equal to 1. Okay, so this is how it is different. So in order to maximize this, we have seen we have to write the Lagrangian. So what we do is we say L of theta, okay, plus lambda times 1 minus pi 1 minus pi 2. So this is my Lagrangian, and I have to take, this is my Lagrangian. Okay, and I have to take the derivative with respect to that for each of the individual parameters and see what we get. Okay, so there's going to be a bunch of algebra here. So I will go through it one by one. So if at any point you have any questions, you feel free to interrupt me. Okay, so now I'm going to just do it one by one, take derivatives and things like that. The form of F1, okay, in the example that I have chosen is normal, but it can be general also. Okay, so now let us first completely focus on Gaussian mixture models. Later on, you can try, I will ask you to do actually Bernoulli mixture models also, okay, when you are doing your assignment. So you will see a lot more types of this later. Okay, so but right now, there is pi 1 and pi 2. This is the probability of belonging to one cluster. Pi 2 is belonging to another cluster. We are mixing two Gaussian models. In general, you can mix any two models like this. Okay, so right, so let us take the derivative of the Lagrangian and set it to 0. So and then we will see what happens. Okay, so first taking with respect to, let us do it with respect to some mu j. Okay, j, so So taking the derivative of this entire thing with respect to mu j, what do I get? So when I take ln, when I take the derivative, I will have 1 over this, right? So let us write that. Mu1 f1. Okay, I'm not writing the whole thing just for ease, but you understand that it is, this whole thing is over here. I'm just not writing it. And now once you have done that, you come over and try to take with respect to mu j, whichever mu j can be, j can be 1 or j can be 2. It's a general thing that I'm writing. Okay, so derivative of the Lagrangian with respect to mu j, okay, where j is equal to 1 or 2, either of the two, the same steps will hold. Okay, so if I take the derivative of this f, okay, so what will happen? So f is, if you remember, let me write this once so that you all remember. Okay, so this is mu1 e power minus half x minus mu1 whole square, xi minus mu1 whole square by, oh my god, I should write it a little more clearly. Okay, so this is xi minus mu1, okay, whole squared by 2 is already there, so sigma 1 squared. So this is what is each of these terms. So if I am taking the derivative with respect to this, what will happen? So this whole thing, since it's e power something, this will anyway be there. So we will write this as fj of this fj of okay, xi. So there is summation, okay, because there are different values of xi. So I equal to 1 to n. Okay, fi of xi given mu j sigma j squared. Okay, and of course the pi j is also going to be there, right? So I'm taking the, first I take the derivative of ln, that is why 1 over ln this comes. Then I am taking derivative of this pi I anyway is a constant, it comes. And then here, when I'm taking derivative of a e power something, that will come. And now we have to take the derivative of the inside thing with respect to mu j. So what happens? So there is a negative, okay, negative half is there, but you will take 2 times that. So this 2 into this n minus 1, right? So, and then there is a negative mu j. So that negative and this negative becomes cancels out. So what you are left with is xi minus mu j. And yeah, this will be sigma j. Okay, so this is equal to 0. Did you understand all the steps here? Does everybody follow this? Siddharth, is it okay, these steps?
Sorry, I'm thinking.
Okay, so I just took a derivative, nothing special. Okay, just you see if everything makes sense.
So that's sigma j square.
Denominator is sigma j square. Thank you. Okay, so that is what it is. Okay, so I'm leaving it for you to interrupt me if things are not clear. Okay, so moving on, now I will try to take with respect to some sigma j. Okay, so sigma j when I'm trying to take derivative. So let us write that, the second Lagrangian. So okay, so this again j can be 1 or 2. In general, it can be up to the k clusters that you are having. The same thing happens for the first time when I take the derivative, it will be 1 over that. Okay. See, go back and try to do this once yourself. Okay, this is an important method worth learning properly. It appears everywhere. Okay, so now after that, I have to take derivative for this fellow. Okay, so again pi pi j will be there because it's a constant. And then when I'm taking derivative for a terms like this, the sigma appears twice, once over here and once over here. So let us try to do it step by step. So let me do it here. Okay, so let us try to take just a minute. What is this? Rectangle select. Oops. So let us try to take d by d sigma of this term. Okay, so let us do it here and then we will put it separately. Okay, so this is a product kind of a product rule. So what happens? So you will have first when I'm taking over here, so this will be minus 1 over sigma squared will come. Okay, 2 pi, and this term will be as it is. Okay, I'm doing product rule. So if you don't remember the product rule, you ask me. I will try to explain it. Okay, so nothing is out of bounds. You can ask anything. So this is so you remember d of d by dx of uv. Okay, so it's nothing but u dash v plus v u dash. Okay, u dash v plus u dash v plus uv dash. Right, that's what it is. So that's what I'm doing. So I took the derivative of this term first. Okay, then I'm trying to take the derivative of the second term. So that will again be plus 1 over sigma 2 pi. E power thing will be as it is. So this is sigma 1. Okay, e power this. Okay, and now I'm taking for the inner fellow. Okay, so there is a into half, minus half will be there, minus half. Okay, then okay, I'm running out of space. So let me write this term over here into this into. Okay, so this into what is this? So I'm taking for the inner shell. So minus half x minus mu 1 whole squared will be there into minus 2, okay, by sigma 1 cube. All right, so now we can do some simplification. Okay, so what we will do, this entire derivative will be, this is f1 of x I given mu1 sigma 1, okay, divided by sigma. So this is like almost like your exponential density with extra sigma over here, right? So we will write it like this, plus, okay, this two everything gets cancelled, and this is again same f1. So f1 x1 mu1 sigma 1 divided by, this is cube. Okay, and yeah, so this is sigma 1 cube. All right, so this is what it is. So we can come back to our original form that we were working on. So this one will actually be sigma j fj. Okay,
So we also have x minus mu1 square in the multiplication.
where?
So in the second term, with sigma.
Yeah. Thank you. Yes, just thank you. So this is also there. So let us write it in colors. See, I can skip all these things, but this is such an important thing that you should all get convinced about it. Okay, so that's why I'm doing this. See, I can look at the book and do it, but I'm doing it in front of you so that you can all see. All right. So then, thanks for pointing out. So that's why I'm making mistakes, because I'm doing it right here. Okay.
So
And
negative
in first
sign.
term,
Sorry.
it should be negative sign in first term.
First term, there are two negative signs, right? Wait. So here, there is a negative here, no? This one.
Yes.
Okay, correct. Thank you. So again, that is another thing. So this will be minus 1 over sigma j, right? Correct? Plus x minus mu j whole squared okay, by sigma j cube is equal to 0. Phew, that was quite complicated. All right, so is this okay, everybody? Whoever pointed out mistakes, are you okay with this?
Yes, sir.
Okay, so there are two things that we have derived. Okay, so this is the first guy, which is for muse. This is the second guy for sigma, and then we also have to do for the third fellow, which is for the lambdas. Okay, so lambda is also a part of this, right? So we have to find for that also. So not lambda, I meant pi's. Okay, so pi is also something we need to estimate. So we have to take the derivative with respect to pi as well. Okay, so it is looking quite complicated, but we are going to do some simplifications and then things will become extremely easy. Okay, so just bear with me. If you are convinced so far that everything is correct, it looks hairy, but it is actually going to be easy. So the third one, let us do it. So d of the Lagrangian with respect to some pi j. Okay, so j again can be 1 or 2. Okay. So now when I'm taking the derivative, the first one will be there, 1 over this will come. So let us do that. So this is summation I equal to 1 to n. Okay, 1 over pi 1 f1 plus pi 2 f2. Okay, now everything will get cancelled except pi j fj term. That derivative we will get as it is, fj xi mu j sigma j squared. Okay, that is what that is, and pi j is gone. Okay, so this is from the first term, and from the Lagrangian part what you have is minus lambda. Okay, whichever is j minus lambda is left. Okay, is equal to 0. So now these are the three equations. Now what we are going to do is we are going to actually solve for each of these parameters. So what is the one thing that you see which is repeating everywhere? Can someone point out and say what is the one thing that repeats in these three things? Just make a guess, right? Even if, yeah. Yes, tell me.
So the summation F5.
Summation, yeah, this, right? This denominator,
Yes.
this whole thing seems to be repeating, right? Here there is a pi j missing, but we can add that. So let's do that. So what we will do is denote. Okay, so let us say denote pi j fj xi mu j sigma j squared divided by pi 1. This time I will write fully. Okay. This whole thing, I will denote it as gamma ij. Okay, this is gamma. So I will denote this thing as gamma ij. Okay, then if you see our three expressions. Okay, so let me write over here with a different color. So our three expressions now become. So what do you get? So first one was here, right? So this was the first one. So this is gamma ij, sum over I equal to 1 to n gamma ij. Gamma ij, and then x minus xi minus mu j by what is there? Sigma j squared, right? So that is there. Squared, this is equal to 0. Okay, remember we are trying to estimate for all j, let us not say for all. So j is equal to 1 or 2. Okay, so in general it can be anything. So this is the first expression. So let us do all the three, and then together let us try to estimate the values. Okay, so now I equal to 1 to n, second one, what is that? So gamma ij times 1 minus 1 over sigma j plus x minus mu j squared by sigma j cube. I hope this is correct. Yes. Okay. So this is equal to 0. Okay. So all this j equal to 1 or 2. Okay. Now what is the third one? So third one is pi j. I will multiply and divide by pi j so as to get gamma ij back. So I equal to 1 to n gamma ij by pi j minus lambda equal to 0. Okay. So is this three expressions fine? Everybody is convinced with this? Okay, so what is it that we were trying to do? So much algebra we have done, but we have forgotten what it is supposed to be doing, right? So let's recall. So whole business was we are given points x's from this mixture. Okay, this is a Gaussian mixture, but in general it could be anything. Okay, and then we had a problem because what we saw is our previously when we did log likelihood and all, everything became products, but now there is a log of summation. This is a difficult thing to do, so we don't know what to do. So we continued algebraically, whatever we could do, we continued, and finally in the middle we have gamma ij. Okay, gamma ij is a function of all the theta. Okay, so if you observe, it depends upon mu1, it depends upon mu2, it depends upon every single thing. So it's a function of the unknown parameters theta. But anyway, we ignored it and just simply wrote what we could write. Okay, now we are trying to do MLE, right? So let us just try to see what you will get anyway. So let us see this. So what you get is mu j MLE is going to be gamma ij xi by summation gamma ij. Okay, this is I equal to 1 to n. I equal to 1 to n. Then our sigma j MLE. Okay, if you do this algebra, I am little exhausted doing algebra, but if you just rearrange things and everything, what you will get is this is equal to gamma ij x minus mu j, where I will put mu j MLE itself, whole squared by summation I equal to 1 to n gamma ij. Okay, so this is mu j MLE. And here you have to be little bit careful. What you do is you have to, if you remember how we did this for multinomial, we solved for lambda. Okay, when you solve for lambda, you will get solving for lambda, we get lambda equal to n. Okay, that you can check later. So basically, what did we get? Mu j MLE is going to be summation I equal to 1 to n gamma ij. Am I audible? Hello?
Yes, sir.
Okay,
Yes,
so these
sir.
are the,
Yes, sir.
yeah. Okay, so these are the three things we will get. Okay, so I have skipped some steps here, but okay, this you can try at home. So there is a problem, right? So in order to estimate mu j, gamma j, and pi j, I need to know gamma ij. Okay, but gamma ij, what it was, if you see, gamma ij was a function of mu j and sigma j anyway. Okay, so there is an issue here. Fine. Does everyone see the problem? Hello? Is the problem clear to everybody? What is the issue? Can I just quickly see if everyone is following me so far? Can I just have a quick poll till this point? Everyone follows me? Devyani says yes. What about others? See, there are 13 people, so you can use this opportunity to really learn it. Yeah, tell me.
What problem are you talking about? I could not get it.
The problem is, see, I want to estimate mu j, sigma j, and pi j, right? Is that not what we want to do? Devanshu asked me.
Sir, I want to know, like, do we need to estimate like all the three? Like, if the distribution is given to us, like, do we know the pi values or not?
No, we don't know. See, okay. So you have okay, little bit, since we have see what we have done is, let us just recall. Okay, Devansh, your question is good. It is a good time to really recap things. See, basically in base classifier we saw that we need to have priors and we need to have class conditional densities. Okay, and once you have priors and class conditional densities, I showed you that it is an optimal thing. That is the best thing you can do for classification. Okay, but now there is a problem, right? So in real life you will not know the exact parameters to start with, so for that we have to do estimation. Do you, this much you are able to follow, right, Devansh?
Yes, sir.
So now what I am saying is, in general, it is not very correct to assume that there is a single density which governs all the class conditional density. So given, say, for example, the height of women, it may not be necessary that it's a single peak thing. Okay, within the population of women, there are people who are having different gene pool, right? So some genetics makes people taller. Some, it's like depending upon which region you are. Possibly, I'm saying, this is all speculation. Okay, don't assume that I'm saying something like this, but it's just for our assumption that there will be different subgroups of people, and each group of people will have different characteristics. So that way we get a mixture. Is that also fine with you, Devansh?
Yes, sir.
So assuming that there is within one class there are multiple modes, I want to really, if I have to use it, I have to have the class conditional density, right? So if you remember, we chose some particular class based on the maximum posterior, right? So we did this Qj Fj by Q1 F1. This is what for, sorry. I'm sorry. I said that the posterior Qj is equal to Pj Fj by summation Pi Fi, right? This you remember? I equal to 1 to K, whatever this is.
Yes.
You remember this, right? So
Yes.
in order to do this, we need to know Fj, and in this case, Fj is governed by 3 parameters: pi, mu, and sigma. Okay, so I need to estimate these parameters before I can even use it in a base classifier. Is that okay?
Yes, sir, I just want to why do we need to also estimate like pi? Because mu I and sigma is clear, but like pi I cannot understand.
No, no. So mu I and sigma I, there is one mu I and sigma here, mu I and sigma I here. Okay, pi is telling in what proportion are the population coming. I don't know how many. See, what if my actual distribution is almost Gaussian, but there is a small bump. This is my pi 1. So then the whole my whole analysis will be different, right? See, this is the proportion pi 1, this is the proportion pi 2. Okay.
Okay, sir. I got it, sir. Yes, sir.
Sure?
Yes, sir.
Okay, so that is why we want to really estimate all these parameters, pi's, mu's, and sigmas. Okay, so now what I'm saying is, when we did all the algebra, what we saw is mu j, sigma j, and pi j we can estimate as gamma ij, function of gamma ij. But gamma ij is also a function of mu j and sigma j. Harsimran, do you follow now?
Yes, sir.
So the problem you understand, right? They are dependent. So I want to maximize this. If this is known to me, gamma ij is known to me, I can solve for mu j, sigma j, and pi j. But in order to get gamma ij, I should know mu j, sigma j, pi j. Okay, so it's basically one in terms of other. Both these things are coming together. Okay, so that is why we are having a problem. The problem is we are trying to maximize a bunch of interdependent variables. Okay, so that is the whole issue here. So what we will do is we will do it iteratively. Okay, so that is what we will try to do. Okay, so the proposal is do iterative things. Okay, so what we will do is, so let us do this. So one, we will say choose theta 0, okay, equal to, what is this theta 0? Theta 0 is equal to pi 0, mu 0, sigma 0. Choose this randomly. Okay, so this is what we will do first. Then second, repeat till convergence. So t goes from 0 till whatever times required. Okay, repetitive convergence. This is our loop variable. We keep track of it. And then what we will do is we will first estimate gamma ij of t plus 1. Okay, what is gamma ij of t plus 1? We know that. Okay, it is this. So let us do that. So what is that? It is pi j of t fj of okay, so let us xi mu j sigma j squared divided by there are two of them, so let me write like this. So k equal to 1 to 2 pi k of t fk of xi mu k sigma k squared. Okay, so this, what is this thing we are using? We are using the teeth one, the teeth estimate. Okay, like this. And then this is called as the E step. Okay, then the second is we will do the M step. M step has three things. Three things we need to estimate. What is that? It's all over here. So mu j, sigma j, and pi j. So mu j of t plus 1 is gamma ij of t plus 1, because we got the previous thing is ready here. Okay, so we can use it. Gamma ij of t plus 1 times xi I equal to 1 to n divided by summation I equal to 1 to n of gamma ij. Okay, this is mu step. For mu j of t plus 1. Then similarly, sigma j of t plus 1 is equal to I equal to 1 to n gamma ij of t plus 1 times xi minus mu j whole squared by summation gamma ij. And the third one is pi j of t plus 1 is equal to gamma ij by n. Okay, so let me just try to repeat what is going on. Okay, so basically what we will start is we will choose these parameters randomly. So mu 0, sigma 0, and mu 0, sigma 0, and pi 0 we will choose randomly. Okay, so for a given iteration, suppose when I am trying to do this for gamma ij of 0, gamma ij of 1, okay, when I am trying to do it for gamma ij of 1, I know pi j 0, whatever I have chosen randomly, I know that. Okay, for basically what I'm saying is, what is this one, you know, if you see this is completely dependent upon xi and mu 0, sigma 0, and all the mu 1, sigma 1, and so on. So we can compute this completely. Okay, so this is my E step. This is how did we choose this? Why did we write this as the E step? That is what essentially we denoted it as gamma ij, right? So that's why we are choosing it as trying to do this as a E step. Okay, why it is called E step we will see later, but essentially fixing theta 0, I can estimate gamma ij. Then I will fix this gamma ij and try to estimate mu j, sigma j, pi j. Okay, so this is all for, we will do this all for j equal to 1 or 2. So we will do the same steps for j equal to 1 or 2. Okay, and then we will do this till convergence. What is the meaning of convergence? If these parameters are not changing, either of the two things that we saw in k-means, we can use the same thing and stop. Okay, so in k-means we saw, right, like you see how much gamma ij is, you either see how much gamma ij is changing, or you see how much each of these things are changing. If it doesn't change much, you stop. Okay, so this is what is the proposal, and this actually works out. Even though it doesn't seem to be very strong, this actually converges. Okay, so there is a proper reasoning why this convergence happens, and we will see that in the next class. But yeah, so this is what is the EM algorithm. Okay, So are there any questions here? Okay, so if there are no questions, let me stop here because a lot of you are missing. I mean, a lot of you are have not attended this class. So again, we will start this on Tuesday and we'll continue from here. So this is a fairly general algorithm. You will see that this has more applications in other areas also, and we will try to give a general EM algorithm, and we will try to prove, no, we will prove why it works also. Okay, so that all these things we will do in the next class. Okay, so let me stop here. So those of you who have any questions can stay back. Otherwise, we will stop here. Thank you, everybody.
Sir, how do we break it down into that iterations? I get the intuition, but I don't see it clearly.
Okay, so where here?
Yes, sir. The iterations, like how do we hide that equation and then we do it by iteration. We are doing it by.
Yeah. So basically, you have theta 0, right? So I can estimate gamma ij of 1. Is that okay? It completely depends on your pi j 0, mu j 0, all these things, right? This is okay, right? I can do this.
So, but
Assuming
that gamma ij will be for that pi 0, mu 0, and sigma 0.
that is correct. So you are assuming as though that is correct. You are right. So this gamma ij is as though as this is for that particular theta 0. It is fine. Okay, but there is a then what I will do is I will treat gamma ij as though that is something that is fixed, and then I will try to do it for the next theta 1. Okay, this I will try to do.
So, but this equation doesn't hold. We got that equation for the same mu and pi. That
okay
equation.
So this is this kind of a thing is called as Gauss Seidel. Okay, this is a general step of algorithm. Okay, so suppose if you want to maximize like two interdependent things. Okay, so suppose if x is some function of y and y is some function of x. Okay, so something like this happens. Okay, then what you try to do is, so this is also like that, right? So gamma is function of theta and theta is a function of gamma. Okay, so what you do is you fix y, you maximize x, then you fix x, and then you maximize y. This is a iterative algorithm that we do. It is not guaranteed to work in general, but for this particular case, we will give you a proof why it is working.
Okay, sir.
So, but I know your difficulty. It is they are interdependent. This doesn't make any sense. Why should we even do this, right? That's what you are asking. But there is a proper proof for it. We will do it next class. See, if you really step back and look at k-means also, right? What is the meaning of this? Choosing this randomly, and then this is also equally baffling, right, Siddharth?
Yes, sir.
Yeah. So you will see why all of these things works properly on Tuesday.
Okay, sir.